Today's lesson is on piecewise continuity. Piecewise continuity. The learning target is I can determine whether a piecewise function is continuous slash discontinuous at a point. So we're going to do a few examples together, about 3, and then you'll be having a task where you get to practice your skills. So let's go ahead and begin. Alright, so here's a sample of a piecewise function. A piecewise function is a function that's defined in certain parts. For example, this function f of x, get my mouse. This function f of x is defined as the square root of x plus 13 only if x is greater than or equal to 3. And f of x is also x squared minus 5, but this one is only if x is less than 3. So you have not been working with piecewise functions written in this manner in this class yet, but you have seen their graphs. What I mean by that is those graphs that have that are parts of different graphs that you guys have been using to determine limits and or continuity. So you've seen the graphs, but now here are the actual functions written down. So let me go ahead and show you just a quick sample. So let's just say that I want to know what the graph looks like. I'll go onto Desmos to see what the graph. So just ignore the work right now. What I'm going to do is show you that we're going to go ahead and graph a piecewise function. So my first one, so this is how you usually do it. When you graph your piecewise functions, you put that curvy little bracket, and then you put your first function, then you put the condition first. So it's x greater than or equal to 3. So the condition is going to be first, it's greater than or equal to 3. Then you put a colon. Then you put your function, and I believe it was the square root of x plus 13. Hold on, let me double check that. Yes, x plus 13. Alright, and then I close my bracket. Alright, so let's just zoom out a bit. So the square root of x plus 13, it's a little bit curvy. You see it starts, the function starts right here as x is greater than or equal to 3. See, greater than or equal to 3 is over here because 3 starts right here. And the function so far has nothing on this side, but that's because I haven't finished typing the other part of the function, which I will now. So again, I'm going to put my brackets. I think the other condition was that it's less than 3. I put my colon. Let me just take a look at my second function. It's x squared minus 5. So x squared minus 5, and then close the bracket. Alright, so this is what my function looks like. So as you guys remember, Desmos does not show you removable discontinuities. Removable discontinuities are when there are holes in your graph. But we know that there are no holes in my graph because I have this greater than or equal to 3. So this top function, the green function right here, is defined when x is 3 right here. So therefore, I don't have to worry about removable discontinuities. Visually though, if I was to ask you if this function was continuous, you would say yes, because as you can see, if I was to trace this, I don't have to pick up my pencil. I just go straight across and on into infinity. All right, so the real question is, how do we use math though to determine if this function, this piecewise function, is continuous or not if I don't have a graph? Because that is what you want to do. Determine if the functions are continuous or not when you do not have a graph. I'm going to show you the technique. So as you notice, the limit to the left side is, what is this? Sorry, that's for the purple function, but the limit to the left side is 4. This purple function is approaching 4. It's not defined at 4, but it is approaching 4. And over here to the right side, this top function right here, the green function, is also approaching 4. So therefore, to determine if a function, a piecewise function, is continuous or not at a certain location, in this case around x equals 3, what you want to do is find out if the limit on the left side and the limit on the right side are equal. That's going to be our technique. And that's it, basically using the graph that I kind of just showed you. All right, let's go ahead and check it out. So let's see if the left This is actually my right side because x is greater than or equal to 3, and this is my left side. So let's start with our right side. So let's first plug in 3 into my right-sided function here to see what the output gives me. So this is just a process. Let's see. All right, I get 4. So on the right side, remember we looked at the graph. We saw that the function was indeed approaching 4. Let's go ahead and check the left side now, this function right here. So if this function right here, if I plug in 3 and it's also approaching 4, then I know that this function will be continuous. Because as we just mentioned, we don't have to worry about removable discontinuities because we have an equal sign here. If there was no equal sign right here, greater than or equal to right here, then we'd have a problem. But as long as the left and right hand side limits here are equal, then you have a continuous function otherwise. Let's go ahead and plug in 3 to the left side. 9 minus 5 is 4. And again, that agrees with what we just graphed on Desmos. We just saw that the left hand and right hand limit were both approaching the value of 4 on the visual graph here. And the number that we got is also the same. That is how you're determining if these piecewise functions are continuous or not without using a graph. All right, let's go on into our next example. So this example is an example that I took straight from IXL. It's asking if this function is continuous at x equals 10. All right, first, let's make sure we don't have any removable discontinuities. Again, we don't because we have this equal to sign here. This equal to sign basically means we don't have any open holes because it's closed at x equals 10 due to this function. All right, so this one's my left side and this is the right side. So with my right side, this is actually your left side in reality. Let me just fix that. Call this left and right. It doesn't really matter as long as you're checking that both of them are approaching the same limit, but I like to be precise because I know x less than 10 is on the left side because it's less than. So we're going to start with our left then because that's what they give me first. They give me the left side. All right, so let's go ahead and check it out. I get negative 12. All right, now let's check the right side. As x is getting greater than or equal to 10, what's happening to my function? Well, my function is just equal to 14. It's a constant horizontal line there. So since there's nothing to plug into, 14 is just simply equal to 14. So because my left-hand side limit is not equal to my right-hand side limit, your function is not continuous at x equals 10. By the way, if you were to try to test this out on Desmos, you'll see that there's a break in your graph, and you'll see that it is not continuous. All right, let's go ahead and move on to the last example. So these examples right here, we're just determining whether a function is continuous. We need to move on to the next step, finding variables such that your function will become continuous, like this one. So this is a question from an AP Calculus exam that I took. You're always bound to see one like these. So it says find the value of k so that the following function is continuous at x equals 3. So again, it's saying x equals 3 because that is where a possible break in the graph will occur. We don't know that yet until we test out the left and right hand side. So that's why it's saying it. But this question is interesting because it's saying find the value of k, and k is right here. For what value of k is this function continuous? So we have to find the value of k that will make this function continuous. All right, so let's go ahead and let's start with our usual process. So this is starting with the left. Good, I put that correctly there. All right, so this is our left side, x less than 3. You're going to go ahead and plug in 3. And I know many of you might think, well, why are we plugging in 3 if this function says x less than 3? It's not defined at 3. No, it's not, right? But I'm plugging in 3 to check if it meets up with this function that is defined with 3, just in case you were wondering about that portion. All right, so I plugged in 3, I get 8. So my left-hand side limit, I get an 8. Let's go ahead and plug in 3 into my x value right here. Remember, k is a constant. We're trying to find k. All right, 2 times 3 is 6, so you get 6k. Good, so I have my left-hand limit is 8. my right-hand limit is 6k. The question is, find the value of k so that the function is continuous. So I know that my left-hand limit and my right-hand limit must be equal. So what I'm going to do is, using mathematical language, create this equality, because that's what I want. I want the left-hand limit, 8, to equal the right-hand limit, 6k. Because if I have them that they are equal, then I know I have a continuous function. So let's go ahead and solve for k. Divide 6 by both sides, reduce your fraction. So when k is 4 over 3, that is when I have a continuous function. Basically, if I was to take this k, 4 over 3, I plug it into here, I'll get 8 over 3x as my function down here. And then if I was to graph this on Desmos, you'll see that your functions will meet and you will create a continuous function, a continuous piecewise function. So that is how you do these types of examples. You're going to go ahead and move on to the task now, and good luck.